right, so 5 in the afternoon, even a bit later. We're late by a minute. So 5:01, what is it in mainland China? 3, and in India, 12:30. We do have somebody from India here? I think so. Maybe not just yet. Anybody in any other time zone? I like the time zones thing. No? Okay. Yeah, so this week you have, actually, let me open the course website. I'll do it on the iPad here since this is what I'm sharing. Right, so you've all seen, I hope you've seen assignment 1. Quite a lot of things to do in the assignment, not a huge number of things, but there are things to do. So in the next 2 practicals, that is this Friday and next Friday, as you can see, what the schedule says is you will get help for assignment 1. So you can ask questions, but also Amina will kind of do some structured problems related to the problems of assignment 1. Okay, somebody slept for 16 hours. I'm very envious of you. That's not nice to tease everybody else like that. So any questions on the content from where we stopped? No? All right. So we did the k-means example. And as I said, these things, that's an example, right? And I'll just continue straight from where we stopped. So it's an example where in the end of every unit, in this case, this is unit 1, what we do is, so this is, sorry, I'm scrolling here like mad. This is the end of unit 1. So what we do is an application. So you saw this application. It's not really part of the material, but the main point, what part of linear algebra did we use for the application? I mean, what from the things we used, did we use matrix multiplication in k-means? What was the one specific thing dealing with matrices and vectors that appeared in k-means? Just a norm, right? Thank you. So all we knew is that if x is a vector and that's a data point, then that's the norm of x. But more importantly, what you could do is a norm of x minus y. And that is what you would call sometimes the distance between x and y. Okay, so the distance between 2 data points was the main thing. And then data points that live in this multi-dimensional, so I'll draw here 3 axes. That's all we can do. But maybe we have a higher dimensional Euclidean space. So the vectors that lie, each one of those points is a vector. The vectors that lie near each other, their normal difference would be small, and then they would be clustered together. Okay, that was a general thing. That's already a powerful tool. But now we're going back to boring land. I'm sorry. But still, maybe you might enjoy this mathematical review. Now there's a comment, Wolfram site is not working. What do you mean Wolfram site? What Wolfram site are we speaking about? Your Mathematica license server or? No, if you have more specification, please do. We will use more Mathematica today. Okay, so we stopped here in matrix multiplication before we move to this kind of thing with the k-means, and let's now get to the next thing. The next thing is a transpose. Okay, so the transpose of a matrix, or maybe I did this, I forgot. But anyway, it's so quick, we'll just do it. The transpose of a matrix just takes a matrix and flips it in the sense that the rows become the columns and the columns become the rows, right? So you always, if this is a matrix, let's say if this is a matrix, you take it according to this point and you flip it like that, and you flip this like that, and it'll become this matrix, okay? So everything that was a row here has become a column here, and everything that was a column here will become a row here. That's what the transpose does, okay? And basically it's just a matrix where the aij of the transpose, you see it's the aji. See, the j and the I have changed their role. That's all the transpose is, but it's very powerful. So many things we just do with the transpose. Okay, some properties of the transpose. This we didn't do. So if you take a scalar times matrix. So you take a matrix A and you multiply it by the scalar alpha. This thing is a new matrix, okay, right? It's a new matrix with every entry scaled by the scalar. So the transpose of this new matrix, well, of course, because what you have here, look, you have A alpha A transposed, the ijth entry of that, according to the definition of transpose, was alpha A ji, okay, and that means, so that is alpha times A ji, and that is the that's the entry of the transpose, okay, alpha times AJI. So there's nothing to this property. The next property is also trivial. If you add two matrices and take their transpose, then that's like adding the transposes, because you add them normally or you add them in the flipped manner. Okay, that's all it is, right? So nothing more to that. How would you call this property in words? Say something in words that describes this property 3. Everybody tired today. In words, how would you say property 3? So there comes a point in the lecturer's life, during the lecture, that if he asks a question, there's like their indication, I start to worry. Maybe the line is dead. Maybe all the, oh, good. Yeah, reversible. Yeah, reversible. Sure, that sounds good to me. It's reversible. Okay, no idea is also a good answer. So it's the no idea property. No, it's a property that you just undo it, right? Transpose, undo it. It just reverses it. You flip between the transpose and not. And that's obvious too. Now, it's this last property which you need to think of a bit and see why it holds, but it's an important property and just plays a role in so many things, okay? So let's just do an example with this one, okay? So we'll do an example. Oh, hold on, let me just explain it. So when you apply the transpose, basically you flip the order, okay? So the transpose, the way you say this property is the transpose of the product is the flipped product of the transpose, right? Because matrix product, we know that in general, AB does not equal BA. When we say in general, that means so many matrices AB will not equal BA. Okay, let's go to Mathematica just for the fun and see an example of this. Sorry, growing pains with my setup here. Stop share. The first property, alpha means the normal number. Alpha, yeah, is a scalar. Yeah, the word you mean is a scalar, yeah. Alpha is a scalar. That was the assumption there. Let's see. Sorry, I still didn't launch Mathematica, but I'm connected to the VPN. Uno momento. Okay, let me share this. All right, so let me now set the matrix A to be, oh, you cannot see, is it? Is that the case? A to be, I'll put it at 150%. So let's set the matrix A, and now let's go symbolic. Let's do A, B, C, D. Okay, so we did things numerically with Mathematica before, but the real strength of Mathematica is that you can work in a symbolic manner. So that's a matrix A. So Mathematica didn't shout and say, hey, I don't know what little a is or what little b is, etc. It just treated them as symbols. And later we can replace them by numbers if we like, but often not. Okay. So, and let's call the matrix B. Let's do the same thing for the matrix B. Okay, actually, let's make this just a bit more interesting. So let's make it A, B, C, D, E, F. Okay, and let's make the matrix B B, C, D, E, F, G, H, I, J, K, and L. But that's B. We want here B. Okay. So we've got a 2 by 3 and a 3 by 2. So if we do A times B, let's call this the matrix P. P stands for product, okay? So if you do P and do P matrix form, so it's not nice to look at P like this, right? I mean, it has too many things, but if you do P matrix form, it appears nicer. All right, so Mathematica did this symbolically for us, right? So this was, why is this AG plus BI plus CK? Because this is A, B, C. It's the inner product of A, B, C and GIK. Okay, that's how you get the entries. Okay, so that was P. But we didn't want this P. What we wanted was a slightly different P. We wanted a P which is a transpose of A. Sorry, we wanted. No, let's just keep this as P, and let's call PT the transpose of P, and let's see it in matrix form. Okay. Why is this? Yeah, so P is 2 by 2, so you see this entry DG plus EI plus FK was here, right? You see this? So you got that times that. That was a transpose. Now that was thunder outside, but that's okay. So if we do now the transpose of B times the transpose of A, okay? So you see, I'm taking the transpose of B times the transpose of A. So the transpose of B, what are the dimensions of the transpose of B? What are the dimensions of the transpose of B? My chat has disappeared. 2 by 3, right? And so that's, I'll put in a comment. I'll put like this. I'll say it's 2 by 3 times the transpose of A, which is, what are the dimensions of the transpose of A? 3 times 2. Okay, is 2 by 2 again. Okay, product, and you get that. And so let's call this PT2. Okay, so that's PT2 matrix form. So the 2 is just the name of the other PT. Okay, so this is how we did PT, which was the transpose of A times B, and PT2 is a transpose of B times the transpose of A. So is PT2 equals to PT? Or I should say, does PT2 equals PT? Yes, it does. And we can check that PT equals PT2, and we get it true. Okay, so in a sense, what you had here in Mathematica was a proof for this property, because this was not with any number, but the proof is for 2 by 3 matrices. But you could just extend it to N by P and P by N matrices. Okay. So that's that. Questions about this? There wasn't a whole lot to what we just did, but it was just for you to work with the symbols in Mathematica. Okay, I'll stop the share here and go back to the notebook. There's a comment, a question. When I did the transpose on PT, Mathematica didn't do it, just put transposing bases around the matrix, but I worked out for PT2. I'm not sure, Jared. I'm not sure if I can immediately help. Maybe. Yeah, I'm just, with that specific question, I'm not exactly clear on how to. Okay, the next thing is something we already spoke about, but because I wanted to expedite for the k-means, but let's just see it quickly. So let me also just turn the light on. It's both getting evening and there's a thunderstorm, so it's dark. Okay, so what we have here is a vector, okay? Treat it as a column vector. And this is sometimes how you denote the dot product. I mean, look, there's a dot, okay? So the dot product between two vectors is a vector v and a vector w is just like matrix multiplication of the transposed v and w, okay? It is wrong to put, do not do, this does not equal vt dot w, okay? So when you work with this, either use this notation or this notation for the dot product between two vectors, okay? This one is syntactically wrong because vt is a row and w is a column, okay? So the dot knows how to work on two things of the same size, okay? And this naturally defines v times v, okay? So if instead of w we have v, and that's what you call the sum of the squares, okay? And you can denote that as the norm of v squared, but basically what you'd mean by norm of v is the square root of the sum I 1 to n of vi squared, right? So if you put a square here, that square cancels the square root, okay? And that's how you get this, okay? Is anybody kind of uncomfortable with summation notation? If so, then that's part of the things that you could work on in the consultation hours with me and the practicals with Amina. Okay. All right. The next thing we have happening is the identity matrix, inverses, and determinants. Now, I must say, this is not a course in linear algebra, okay? We're not doing a course in linear algebra. This is just a course in kind of basic mathematics where you're just seeing a few of the basic things from that will then play a role in linear algebra. Linear algebra is how, linear algebra is, you know, about spaces and dimensions and things like that. Now, there was a question and it was answered, yes. So V can be treated either as a vector or a matrix. Thanks for answering that. Okay. So it depends. I mean, when you look at this, you think of V as a vector. When you look at this, you think of V and W as a matrix. I'm sorry if I'm yelling. It's just that the thunderstorm is very, very strong. Who else here is in Brisbane at the moment? Somebody? You have some strong rains? Oh, okay. Well, I'm near the university and it's strong. Yes, it's heading north very fast. Okay, okay. I see everybody got excited about the weather. Whereas the people overseas maybe, okay. All right, so you'll get the storm soon. Hang in there. It's going to pass. All right. An n by n matrix is square. Well, okay, if it's just of order n, fine. And the diagonal are these things on the diagonal. Okay, that's just the diagonal of the matrix. Okay, there are some Mathematica functions for this. We'll see them just in a few minutes. Now, you will call a matrix lower triangular if everything above the diagonal is 0. This is, let me paint this like with green. It's 0, 0, 0, 0, 0, 0. All this is 0. That makes it lower triangular. And you'll call it upper triangular if everything below is 0. Okay? So the lower an apple is this. So just another thing on the weather, exact opposite. It's skin burn season here. It was earlier today. Where are you, KC, if you don't mind sharing? This is now going on this is going on YouTube, so no. Okay. Got you. All right, yeah, this is going on. All right, so that's lower and upper triangular matrices, okay? Now, What's a matrix that's both lower triangular and upper triangular? What would you call it? I mean, the answer is here on this page, but what would you call a matrix that is both lower triangular and upper triangular? It's just a matter of definition, but it is symmetric, but there's something more to say about that. It's diagonal. So a matrix, we're speaking here within the space of square matrices. A matrix that's both lower triangular, so you take your matrix, okay? Lower triangular means all this is 0. Upper triangular means all this is 0. So then it just has things on the diagonal. So that's a big waste of a space to have a diagonal matrix, no? I mean, you could have just had that vector. However, mathematically, we often like to work with diagonal matrices, and I hope you'll see why in a few examples. Okay. So this matrix here, for example, is a diagonal matrix, okay? But you see my point that in terms of the data, you know, it just has these 3 numbers here in the diagonal. We might as well have kept them as a vector, okay? However, there's meaning to having the matrix and diagonal matrix, because it can be, if you multiply it with another matrix, and you're either scaling the rows or scaling the columns. I think we'll see that. Now, the most special and natural diagonal matrix is, there you have it, the identity matrix. What is the 1-by-1 identity matrix? What is the 1-by-1 identity? This is, by the way, the identity matrix, yeah, all ones. So what is the 1-by-1 identity matrix? What would you call it? Or what is it? It's 1. It's a number 1. And the number 1 is the identity. What makes the number 1 identity? 1 times 28 is 28, okay? 1 times -3 is -3. So 1 is the scalar identity. I happens to be the identity matrix because if you take any other matrix, A, and you multiply it by I, you can work out to see that you'll get, well, what's going to be A times I? It's going to be A, okay? And also, if you can do I times A, what are you going to get? You'll get A, okay? Now, there isn't a single I. The I here needs to be of the right dimension. So if A is m by n, okay, this needs to be an n-dimensional I. Okay. But yeah. Okay. And if this A is m by n, this needs to be an m-dimensional I. So sometimes you can put the subscript here to say dimension of the matrix. Okay. Some remarks on the identity matrix, and then we'll go to Mathematica. So here's actually, let's just do this for the 2-by-2 case. Let's do this manually. So this is the A matrix, okay? And now we call the entries A11, A12, A21, A22. Let's multiply by this guy, which is I, okay? So if you take this entry here, what we're going to do is we'll take this row times this column, okay? So that's going to give us the 1 times A11 and 0 times A12, and that gave us the A11, okay? And just to see another row, for example, just for the fun, if you take, this row, say, by this column, that's going to give us this entry, okay? So then you're going to get that 1 times A22 and 0 times A21, and that's going to give you this guy. All right, so that's how the identity matrix works. Now, there is the jth column vector of the identity matrix, okay? So this a column vector here where you've got 0, 0, 0, 0, except for the jth entry, this is sometimes denoted EJ. Now, of course, there's not enough information in just saying E subscript J, because you need to tell me on what dimension you're speaking about, right? So you'll need to say E sub J in, say, dimension 10. So that means that you have a 10-dimensional vector, and this is the jth coordinate vector, okay? So that's that jth column of the identity matrix. It also happens to be the transpose of the jth row of the identity matrix, okay? These are sometimes called unit vectors, all right? Now, let's see what happens when we multiply a matrix A, some arbitrary n by n matrix in this case, by this EJ. EJ in, let me just write R to the power n. Okay, that's like the n-dimensional vector. Okay, that's what I mean by n-dimensional vector. So what you're going to get is, okay, you're applying a matrix to a vector. Okay, that means that you're going to get a result vector. Now, this first row should be, let me highlight in different colors, should be, oops, sorry, do this, should be this times that. But you only selected the jth coordinate. So what you get here is A1j. Okay, that's A1j. Okay, and then if you go to the second column, the second row, sorry, you multiply that again by that. Again, you only selected the jth coordinate. So then that's going to be A2j, etc., up to A and j. So multiplying a matrix or applying a matrix by the identity column selects the jth column from that matrix. Okay, so a lot of things that we do in linear, well, in this kind of working with matrices is sometimes, you know, we want to represent things with these simple things that in one hand look a bit kind of, why would we need this? But on the other, there's actually quite a lot to it. So when you get to MATH7502, for example, you'll see that any linear transformation, any transformation that happens to be additive and homogeneous can be represented by a matrix. So this very simple multiplication that I've just done plays a role with that. Okay. Okay, and this is one way of also seeing that AI equals A. Okay, because then, because when you're applying A but on the matrix I, what you're doing is you're multiplying by each of the columns. There's a question, is it somehow related to partial derivative? If so, only vaguely. So derivatives can also be linear operations, but not really. Does this have a special application? Yeah, so one of the applications here was to show that AI equals A, that I is indeed a left identity. Okay. But there will be more applications of representing a, well, of just doing this kind of very simple multiplication. This is also sometimes called the canonical vector. Again, it's these things that will build up, and then in MATH7502, you use the theory of linear algebra better. Oh, well, 4 things. I'm not sure I said that so well. Okay, you can also do the same if instead of A here, you stick an A transpose, so A transposed I equals A. Okay. So sorry, A transposed I equals A transpose. Okay, and this is a proof for it. All right, this is not the key point, but the point is that the identity times A or A times identity equals A. Right. So that's the identity matrix. But before we move on to inverses, let's just see this in Mathematica. Stop share and start share. No, let me stop share and start share. Let's see. All right. So let's call II the identity matrix of, say, size 3. Okay, so that's II. Okay, and let's call A matrix of random entries now. So let's do a table of random integer on 1, 3, 3 by 3. Let's make this 1 by 5 so it's kind of a bit more exciting. All right, so that's the matrix A. So if you do A times II, naturally we're just going to get A. Okay, so does that equals A? The answer is true. Question. Would we have to learn how to calculate the inverse manually? No, not for this course. And even in the next course, it's done. The manual is not, it's not about the classical tedious manual, but we will do it for 2x2 matrices shortly. Okay. So with that question, let's go on to inverses. So again, there's more things to matrices that you would see if you would do kind of the full linear algebra, and that would be in the next course. Sorry, I'm alluding too much to the next course, but at this point, what we're doing now is kind of just some basic calculations with these things, just so you speak the language. Okay, and today soon we're going to leave matrices and vectors and move on to Unit 2 sets, which is very which is different. Okay, so an inverse. So a square matrix has a property of, so when you speak about inverses, by the way, note, you're only speaking about square matrices, only square matrices. Okay, so within all the matrices they can be fat, they can be skinny, they can be square. We're only speaking about squares. Within the squares, some of them will be called invertible. A synonym of that, a different way to say that, is non-singular. Okay. If you can find another matrix B that quote unquote cancels A. Okay. So let's say let's start with 1x1 matrices. What if A is a number 5? What would be a B here? If A is a number 5, what's the inverse of the number 5? I'm talking about 1x1. 1/5, right? And indeed, you know, you often call this thing the inverse, right? In scalars, right? The inverse. So the matrix B, because 5 times 1/5 equals the identity, 1. Okay, so the matrix B plays that role of that 1/5. Okay, and it does it both from left to right. 1/5 times 5 equals 1. Okay, so AB will equal BA, and that would be the identity. And then, well, the fact that in slightly more general terms, if A times B equals I see you can't see this, sorry. Let's change color. If A times B equals I, then B is a right inverse of A. And if B times A equals I, then B is a left inverse of A. But in this, we don't speak about left inverses, right inverse. In this course, just the inverse. But if left inverse is a right inverse and the matrix is square, it's just called the inverse. Okay. So B is the inverse of A, and it's denoted A minus 1, right? This 1/5 is also 5 minus 1. Okay, so the mathematics generalizes this. All right. Is the inverse unique? Yes, we can prove that the inverse is unique. The inverse is unique. It's a good question. Yeah. So you cannot have, let's see, I'll try to prove it by hand in the break, and then I'll show the proof. Thanks for the question. Yes. So just like here, the inverse is unique as well for scalars. Okay. Now, if the matrix is not invertible, then it's said to be singular. Okay. So if you can't find such a thing, can somebody give me a singular 1x1 matrix? What's a singular 1x1 matrix? What's the singular 1x1 matrix? 0. That's the only one, right? So there's only 0 in 1x1 matrices. So 0 is not a variable. You can't do 0 divided by 0. Okay. Well, there's not something that you'll multiply by 0 to get 1. That's more what we should say. Yeah. Okay. So there was a question before: do we need to calculate inverses explicitly in this course? No. not in this course. Computation of inverses is important because solving of system of equations has to do with computation of inverses. In general, many mathematical problems and data science algorithms embedded inside, have some matrix inversion involved. Okay, that's kind of, in a sense, a fundamental problem. And it's also computationally an expensive problem. It's computationally hard to invert huge matrices. Well, it's also hard to store huge matrices, right? I mean, 1,000 by 1,000 matrix, if it's not sparse, has 1,000,000 entries. That's kind of okay, right? But 1,000,000 by 1,000,000 matrix has what, 1,000,000,000,000 entries? That's already a bit too much, okay? And you can't compute those in inverse for such a matrix explicitly. In general, you need about n cubed operations to compute the inverse. Do you need to know the determinant of the 3 by 3 matrices? Yeah, but with not much focus. We'll get to determinant. We didn't get there yet. Okay. But here's one we'll see. So take the general 2 by 2 matrix. Okay, A. Okay, and there's a claim here. There's a claim that this is the inverse. Okay. Now, to see that B is the inverse of A, there's a way. How did you find this, right? Now, by the way, let's just see the rule. So look, we've got the A and D. The A and D flipped. So let me change. I don't know what to do. We'll do this, and we'll do like a little, they flipped. You see these two flipped, A and D, right? A and D flipped. We'll see why B is that, all right? And the C and the D, the off diagonal, so let's go here to purple, say, the C and the B, right? So there's a diagonal, and this other, the purple one, we call it sometimes the off diagonal. The C and the B, they didn't flip, they just changed sign. Okay, they became minus. And it just so happens that our universe is made in such a way that this is the inverse. Now, you can ask me why, okay? So instead of telling me why, how about I just prove it to you, okay? So how do I prove it? I mean, there's a question how to find this, right? How to find, well, how to know that that's it? Well, we'll get to that later, or we might not even, okay? But let's use Mathematica to prove that this is the case, right? Oh, sorry, by the way, this is not the inverse. This is a mistake. Sorry, A, B, yeah, this is not the inverse. This divided by this number is the inverse, okay? And this number is a determinant, okay? No, B is not called the adjoint matrix, as far as I know. Okay, so the claim is that this is the inverse. So let's just use let's just use Mathematica to see that this is the case. So this will be just another example of the usefulness of a symbolic language. Okay. So now what we have is A is ABCD. You see the sharing? Yes, is ABCD. A matrix form, just to see it. There we go. All right. And let's make our B, it was D minus C minus B A. B matrix form. Okay. So in this B, what we did is we flipped the diagonal and we put negative on the off diagonal. Okay. All right. So if I now do A times B, just see this as a matrix, then we get this thing. What am I doing wrong? A, B, C, D, D minus, oh, sorry, I made a mistake. D, yeah, no, minus C. No, D minus B minus C, sorry. Okay, so this B needs to stay in place, and it just becomes a minus B. All right, is this what the chat was? Sorry, I missed the chat. Okay, yeah. All right, so again, that's A and that's B. And now if I multiply, okay. All right. Now, look at this term here. This scalar and this scalar are the same. Okay, so let's call delta just like it was in the notes. I think escape, capital D, escape, that does a delta. And let's do, yeah, I did escape, capital D, escape, delta, that's capital Greek letter delta. Okay. And let's call that AD minus BC. Notice that Mathematica sometimes puts expressions not in the way that we as humans would put them, right? We would like to write AD minus BC, not minus BC plus AD, but you know, addition is commutative. Okay, so that's the delta. So let's now do 1 divided by delta. So I'm doing control escape, escape times A times B. Okay, let's do all that in matrix form. So what are we going to do when I hit here shift enter? By the way, to do this, I did 1 control divide, and it kind of divided. And another thing, you can never put a matrix on the denominator. So when you see an expression like the denominator is the bottom of the fraction, yeah? When you see an expression like this, you know this is a scalar. You can't put a matrix there, just so you know. Okay, so what are we going to get now? Oh, okay. So the question is, there was a comment before. We're going to see unit, but somebody says, shouldn't it be 1 on delta times B? Well, I agree. I agree that what our claim is that, you know what, that the inverse, so let's actually take it. This will actually be the identity. But the claim is that the inverse is this B divided by delta. Sometimes when we say divided, it's called normalized. But this 1 on delta is a scalar. So scalars can come out of matrix multiplication freely. Okay. So let's first do this and see if it works. That doesn't seem like the identity matrix, is it? Is this identity? What are we seeing? It is. It is. And if it isn't clear, it is. Well, you see that you have this here. So what you can do is you can do maybe a simplify or a full simplify. Let's see. No, it still decided not to do this because it was afraid of if AD minus BC is 0. Okay. So basically the inverse, the inv B, let's call it the inv A, sorry, the inv A was 1 on delta times B, okay? And then A times inv A gives us the, I wonder if we do this now, full simplify or just simplify. Yeah, Mathematica doesn't want to simplify this. Unless maybe in older versions they used to, because it's just not sure if AD minus BC is 0 or not. Okay, let's see, maybe there's a assumptions. No, sorry, simplify. I'll just do help on simplify. Yeah, okay, look, so if I do simplify and I'll tell it AD minus BC not equal to 0. Let's see, I think this might work. Okay, now let's go to the help of Mathematica. Local. Now this opened another window that you can't see, so I'll share the whole desktop for a sec. There you go. So how do we work with assumptions? So go here, options, assumptions. Simplify. Oh, okay, we need to do assumptions like this. We need to do assumptions. And maybe that still didn't work. Why not? Maybe without this set, without this listing. No, okay, I'm not sure. It's full simplify. I should stop because it's not working. But anyway, still we saw, unless somebody can get this to work for Mathematica to actually simplify this to just make these ones. But I failed. Doesn't seem to be very user-friendly. Indeed, Mathematica and sometimes might not be very user-friendly, but it's kind of powerful. So that's why you're playing with it in this course. Again, the main motivation is not the linear algebra in this course. The main motivation is the fact that later in the calculus, you could do things symbolically. Okay. So this is how we proved by computer. It's not a big deal to do it by hand either, that the inverse of a 2 by 2 matrix, let me share this again, is as given. Now, in this inverse, we need to be careful because we're dividing here by delta. Okay, but it's only going to be the inverse when this delta is not 0. And everything kind of works in the math because this delta is actually going to be, this number is actually the determinant, which we'll get to after the break. And it turns out that the determinant, one thing you do with a determinant is you compute the determinant of a matrix and you see if it's 0, it means, oops, it's not invertible, it's singular. Otherwise it is. There's more meaning to the determinant. Determinant have to do in linear algebra, you'll do in MATH7501. When you're doing linear transformation, the determinant describes what happens to volumes in this linear transformation. But if the determinant is 0, it means when you're doing linear transformation, you're actually collapsing from collapsing dimension, and that's how it works. I think this is mumbling what I'm saying because you're not really learning it here, but at least this is a formula. Now, how would one find this formula? So some of you might say, okay, fine. I mean, you showed us a proof using just calculations by Mathematica, which of course we could have done by hand as well, right? Because you can do this multiplication by hand. This is what was done here. Okay, how would you find out, how would you derive that this is identity? Well, what you would do, you could do it yourself if you'd like, we won't do it today, is you do ABCD times the let's call it the G11 and the G21. Okay, you'd want that to be 1, 0, and you'd want ABCD times G. Oops, I'm sorry. G 1, 2, G22 to be 0, 1. And what you're doing here is basically, this is not working. Anyway, okay. So what you're doing when you're doing this is you're saying A, B, C, D times G11, G12, G21, G22 should be the identity matrix, because this is the left column of this 2 by 2 identity matrix. This is the right column of this identity matrix, right? So these two things are the identity matrix. So you can then, you have here a system of equations. It's at least one way of doing it, right? You have here a system of equations with 2 equations, right? We've seen this last week, and 2 unknowns. Your unknowns are G11 and G21. And you have here another system of equations. It's different, okay? Because the right-hand side is different with 2 equations, 2 unknowns. These are unknowns. So you can effectively solve these system of equations and then find out these entries, and they'll be exactly these divided by the delta, okay? If you do all that manually, okay? And that would be a way to do that, okay? Yeah, other questions, thoughts? Okay, storm has passed me. Anybody in Brisbane still getting the storm? It's now the quiet after the storm. Yeah, oh, I'm sorry about that. Okay, it'll pass too. Okay, almost gone the radar. Oh, and you're passing, and you're tracking the radar. Okay, so it's 5:51 here in Brisbane. We'll continue in 9 minutes. I'll come back a minute or two before to just pick up. So we'll take a break now. See you guys. See you in a few minutes. Hey, we'll start in a few minutes, but if anybody has some questions. So from the people not in Australia, anybody here now in kind of close to 0 temperatures where you live? No. You're in India, right? So that's not the case. Yeah. Yeah, quite a few in China, a few in India, some in Brisbane. 4 degrees, 6 degrees. Okay. Is that the Beijing area? With those cold temperatures? North China? North of China. Okay. Wonderful. $5.58. No questions about the content? 13 degrees in South China. I mean, in Guangzhou and the Hong Kong area, I don't think it gets so cold, does it? It's 13 degrees. I mean, so cold, but. So for you, it's hot and 31 degrees. Ay. Yeah, okay. Guangzhou is 20 plus minus. That's what I figured. I mean, it gets quite south. Yes, so hopefully if you guys can get to Brisbane this year, you get in the months of pretty much April until November or October, extremely pleasant, just superbly pleasant. Yeah, me too. Okay, 5:59. No questions. We've just been speaking about the weather like some boring people. I'm to blame. Okay, now there was a question. Let me see. Can I get an empty page here if I do this? Yeah. So there was a question. A nice question: is inverse unique? Sorry, the writing is kind of bad. Unique. Unique means it's one of, right? So what do we mean? So if we have a matrix A, and let's call B1, so let's say A, and B1 is inverse. So AB1 equals I, and also B1A equals I. That means that B1 is an inverse. And let's say we have a matrix A again, and B2 is inverse. Okay, so A times B2 equals I, and B2 times A equals I. So now, okay, so let's say that A has, this is in a way, by the way, we'll speak about logic starting next week, I think, or maybe towards the end of next week. This is in a sense a proof by contradiction. So assume that A has two inverses, B1 and B2. Okay, it doesn't have to be a proof by contradiction, but in this case, we just assume, say there's an inverse B1 and B2. So now look at B1, A, B2. Look at this product. What is it? What is a product of three? There's a question, logic in the sense of mathematical induction. Yes. What is a product of three matrices? Well, we said that matrix multiplication is associative. You could put the brackets here, or alternatively, you could have put them there, right? So let's do that. So we know that this equals B1A, B2. The brackets can be also here. Okay, that's a 1. Okay. But what's B1A? What's B1A? It's I. And what's AB2? Is I. Hence, that's like an arrow means implies, B2 equals B1. Okay? So that shows you that an inverse is unique. Okay, so this is sometimes called proof by brackets. You kind of use the associativity property of the matrices. That's it. Okay. It's a numeric example. I think I just might skip this. The inverse of 1, 2, 3, 5. So fine. So you just put a minus here and a minus here, and you flip this, and you divide by the determinant, which we'll get to in a second. Okay. So that was a numerical example. Okay. Now, this is an inverse of a 3 by 3 matrix. We're not giving a general formula for the inverse of a 3 by 3 matrix, but if you are given a matrix A and the matrix B, and you want to show that B is the inverse of A, which also means, by the way, that A is the inverse of B, the inverse of the inverse is the matrix itself, okay? Then all you need to do is you need to carry out matrix multiplication, and if you were to carry out this matrix multiplication, you'll get your two identities here, okay? Properties of the inverse. A has at most one inverse. So that means that if an inverse exists, it's unique. That's what we've just shown. If A and B are invertible, then so is the product AB. Okay. And then AB inverse, the inverse of the product is the flipped product of the inverses. Okay. What does this remind you of? Where did we see this pattern behave before? Where did we see, sorry, similar type of pattern before? Just in transposition, right? So now to see this, what you need to do is you need to say, look, here's the matrix AB, and I now want to multiply it by its inverse, okay? What should this be? What should AB times its inverse be? Yeah, AB times its inverse. So I'm going to put a green square around the matrix AB and times its inverse. That needs to be the identity. Okay, that needs to be the identity. Now, look, if we want to get the identity, then what we can do is we can get AB times B inverse times A inverse. You see, this B and B inverse, this gives us an identity. Okay, and then we get an A times an A inverse. And that gives us another identity. Okay, and indeed we get the identity. So this proves that this is the inverse. Okay, this rule for the inverse. A third property is that A is invertible if and only if it's transposed and invertible. And you can actually interchange the inverse and the transpose. And because of this interchangeability, people sometimes denote this A minus transpose, okay? A minus transpose means either this thing or this thing. Either forms are the same, so you can just write A minus transpose. Okay, so sometimes in mathematics we use notation if it makes sense. Okay, that was inverses. All right. Determinants. So inverses are just for square matrices, okay? Determinants are also things that we speak about just for square matrices. So just for n by n matrices, okay? You cannot be explicitly skinny or fat, right? A determinant is a number. It's a number associated with a matrix, okay? The inverse of a square matrix gave you the same type of object, a square matrix. The determinant gives you a number, okay? And we just define it as follows. So if it's a one by one, there's different kind of, if you ever do a more advanced algebra course, so kind of better definitions of the determinant, kind of more natural, but we just define it constructively and we say as follows. For a one by one matrix, the determinant is just like if the matrix is a scalar A, the determinant is just going to be the number A, okay? And by the way, we use this thing, these lines, these black lines that I'm drawing now, that's determinant, okay? But these black lines, we use them in multiple ways, even in your homework assignment. Like if this thing was a set, we'll soon speak about sets. If this A was a set, then this means the cardinality of the set, the number of entries of the set. It does not mean determinant, okay? So we need to know what we're speaking about. Or sometimes you'd put, if you're actually writing the entries of a matrix, you put straight lines like this, okay? So this here, this inside is a matrix, but this outside is a number, and that's the determinant, okay? So you put these straight lines, which also can mean different things. I mean, what else do we do with straight lines? I mean, kind of the most obvious thing in math, the absolute value, right? So it's not some languages, Jared, it's also in university math, this is kind of an extremely overloaded sign. It can mean the determinant, it can mean the absolute value, it can mean the number of elements, okay? So at least in all cases, we know that it gives you a scalar, because you can also, by the way, for absolute value, you can put here a complex number and it'll give you the modulo, okay? So at least in all cases, it gives you some sort of scalar, okay? Some sort of measurement, but it means different things. It should be clear from context. So the big deal with determinants is for a 2 by 2 determinant, a 2 by 2 matrix, you do A1 times A2 minus A12 times A22. So you take the green diagonal and you subtract off that. Let's go back to the formula for the inverse of a matrix, of a 2 by 2 matrix. And now look at this delta here. You see, we did exactly this. We took the, let me use now this color coding. We used this, yeah, this guy, minus this guy, okay, BC. So this thing is indeed the determinant of this 2 by 2 matrix. Okay, so that's determinant so far. Now, in general, if you have an n by n matrix, it's a bit of a pain in the butt. And I'm actually going to skip it because it's not, we don't need it immediately now, and you're just dealing with determinants in a formal manner. Maybe we'll get back to it if we just have time before I depart from you guys in 2 or 3 weeks. But the point is that you compute it recursively. And any of you that have done a linear algebra course have worked on that. So you take the matrix and you cross out entries and you do things and you compute the determinant recursively. And then this is how you do determinant of a 3 by 3 matrix. There are some videos on the website. So if say you go here, you go to unit 1, you go down and you go to determinant. So I actually very much recommend this video about determinants, which actually puts a bit of light in determinant, but that you'll see in, so this video by 3 Blue 1 Brown, but you'll get more of that in Math7502. Okay, so because for our purpose, we just work with determinant very formally. So yeah, we can do determinant of an n by n matrix. Let me actually show you Mathematica a second, because that's another nice thing that you get with a symbolic language. Stop share Mathematica. So let's take now A to be I think I can do this like this. I can do array a. Let's try this. I'm not sure. A I J I 1 2 3 say J 1 2 3. Sorry. Let's just do a table. Yeah, that worked fine. Don't know why I didn't need array. So an A matrix. Okay, so I've got the general 3 by 3 matrix. So look, let's compute the determinant of A. Here you've got a formula. Okay. Now, if you want to see the power of Mathematica, if you want to get a 5 by 5 matrix and compute its determinant, you still get a formula. It's a bit of a big formula. Okay. So it carried out the determinant analytically using those cofactors that I skipped over. Okay, let me just put it back in 3 by 3. Whoops. Sorry. So that's the determinant, or at least a determinant analytically with Mathematica. Let's go back to iPad, share, start broadcast. Yeah. Okay, we're back on there. So all kinds of properties of determinants. And again, I think I'll skip some of them and might move back, might not. So, but some will show. So determinant of the transpose is just like the determinant, okay? So that doesn't change. You see it for the 2 by 2 matrix because this transpose of the 2 by 2 matrix, you see in the transpose, what you did is you just flip these guys, right? You see this is 1, 2, and here it's 2, 1, okay? That's, you flip these guys. But you subtract that entry, so it doesn't matter. Okay, so this thing you subtract, it doesn't matter if you multiply that way in here. Okay, but it holds in general. Okay. Now this has to do with the computation before. You can compute determinant along row and column. Let's not worry about that just yet. Now, when you start to have some structure in your matrix, such as this matrix, which is, what is this matrix? Upper triangular or lower triangular? Well, it says, but here you got zeros. So what is this matrix? It's a lower triangular, but it doesn't matter. If your matrix is triangular, upper or lower, then a consequence of the recursive formula for computed determinant is that the determinant is just the product of the diagonals. Okay, the determinant is just a product of the diagonals. Let's try and play around with this in Mathematica just for the fun, because maybe it will teach us something. Let's see, sorry, again, zoom, stop, share Mathematica. So we've got our 3 by 3 matrix, okay? So let me now take, what I can do is this. So what I can, let's call this, let's even go crazy. Let's go for 4 by 4 matrix. Okay, got a 4 by 4 matrix. This is det A. Okay, this is an expression that fits on one screen. Now let's call this the det A. Okay, this is now an expression, det A. Now let's substitute. You see what I can do? I can do a substitution rule in Mathematica. This is how you do a substitution rule. So you do /dot and it substitutes. So I'm going to substitute, and I'm going to put the subscript. I hit Control and do subscript, and let's make it upper lower triangular in this case. So it's, for example, 1, 2. You see 1, 2 is this entry. Let's make it 0. Okay. So that has zeroed that entry. Okay, so this expression actually simplified a bit because, I mean, it has a, whenever you had a 1, 2, I think that whole term disappeared. Okay, so let's now substitute all these guys to be 0. So how do we do this? Well, we could have substituted, we could have also written comma, another substitution rule. We could have done like A, 1, 3, and put that to be 0. Okay, we could have also done that, but let's actually create this substitution rule as a table, as kind of an entry. So let's let's call it make lower triad equals table A I J going arrow to 0. So that's what's going to be the substitution rules. And we'll go I going 1 till 4, till the 4th line. And J will go from I plus 1 to 4. Does this make sense? Let's see. So it sort of made sense. It's not exactly, but we got the substitution rule. A12 is 0, A13 is 0, A14 is 0, A23 is 0, A24 is 0, A34 is 0. And the last one, well, I maybe we could have just gone I up to 3. Okay, because the 4th row, there's nothing to the right of it. I hope it makes sense of that. Okay, but still, what it gave us is because we had this kind of two entries in the table, we ran on I and ran on J, it gave us a nested list. So let's use flatten to flatten this. Okay. And now these are the substitution rules. So now if you just do det A make lower triangular, that's kind of cool, is it not? I mean, I'm excited. I don't know if you guys are excited. So what we got is we computed the determinant for the general 4x4 matrix. So we worked like slaves. So we computed. Of course we didn't. Mathematica did it algorithmically for us. Okay, but then we now replaced all the things in the upper triangular by 0, and we saw that we just ended up with one term, which is A11, A22, A33, A44. Okay, actually only this term stayed. All the other terms vanished. Exciting. I don't see many points of excitement from the cohort. Maybe you're tired. Maybe. Oh, whoa, thanks. There was a whoa. Yeah. OMG. Thank you. Thank you. Very good. Very good. Very good. Okay. Yes. After these bells and whistles, let's get back to more stuff. Phenomenal. All caps phenomenal. That's the best one. Thanks a lot. I like. I'm being cynical, but no, I mean, this is something that, yeah, symbolic computation is kind of nice. All right, so upper triangular, lower triangular matrices have this great thing with the determinant. By the way, what's the determinant of the identity of a triangular? Sorry, of a diagonal. So what's the determinant of the matrix 3, 4, 5, 6? You don't need to say number and all zeros here. Okay, what's the determinant of that? 3 times 4 times 5 and 6. I mean, this guy is super lucky. He's both upper triangular and lower triangular. Okay, so in that sense, the determinant of the identity is 1 times 1 times 1 times 1, and that's 1. Okay. Okay. So the determinant of a product is the product of the determinant. That's good. All right. It's not true the determinant of A plus B is not, in general, the determinant of A plus the determinant of B. Okay, this is not the case. It holds for products. All right. Now, from this you can see that if A is invertible, then let's just go to this, then the determinant of the inverse is 1 on the determinant. Okay, so that's kind of cool. All right. So that's all we wanted to say about matrices. Let me go quickly and just summarize this thing on how to compute. I thought there's more, but that's so I think we're in time. So when you go to an n by n matrix and want to compute the determinant, one way to compute it is to go from an n by n matrix to a matrix of one dimension smaller. You'll go n minus 1 times n minus 1, okay? So say I'm going to draw a matrix here, n by n. Let's say we got, let's do a 4 by 4 matrix, okay? Okay, this matrix is 4 by 4. So what you can do is you can go to the matrix which reduces, say, which deletes, say, this jth row, j equals 3, and say this, sorry, jth column, it was a mistake, and this ith row, I equals 2. Okay, so then you're left with a matrix like this, which will have these entries which I'm filling out. Okay, so you've kind of said bye-bye to this ijth column, okay? Now, this is all apparent in this notation. This block here matches this block, okay? And this block here matches this block, which, by the way, you can go to the end and then those blocks are empty. And this block here matches this block, and this block here matches this block. So if you take the determinant of this matrix, which is smaller by 1 dimension, okay, then what you get is and you then do this following with a sign. You take the sign and you take -1 to the power I plus j. So -1 to the power I plus j means to go according to this map. So it means that on this diagonal, I plus j, see 1 plus 1, 2 plus 2, 3 plus 3, etc., is even. So you get a pluses, but here you get a minuses. Okay, so this is a way to say it's either plus or minus. So the determinant of this smaller matrix, so we went from 4 by 4, we went to say 3 by 3, is called a cofactor. Now, the determinant of the whole matrix expanded according to, there's many ways to do this, but expanded according to, say, this first row would be a sum of the first 4 cofactors. Okay. Now, there's or n cofactors, in this case 4. So then these now are given by 3 by 3 determinants. And then you can go, oh, from a 3 by 3 determinant, I know how to go to a 2 by 2 determinant because you compute this recursively. And then 2 by 2 determinant, you stop there because you have this formula. Okay. If you guys really push me to a wall, we'll program this manually in Mathematica, okay, by recursion. By the way, this is in no way the good numerical way to compute determinant by this recursion. But this recursion is kind of, you know, the standard way you learn how to compute determinants. Okay, the good way to compute determinants numerically is with something called LU decomposition, which you'll learn about in Math7501. Okay, so that's these cofactors. And then there's this property here that you could have expanded not just according to the first row, you could have expanded according to any row or any column, and it would be the same. Okay, yeah, so that's it. Questions about this? Okay. Now comes this very small subunit dealing with vectors, but we spoke pretty much about vectors. So the order of the text here, I must say, is not superb. So you know, this treats a vector as an arrow like that, okay, where this is V1 and this is V2. Sometimes you can think of the arrows being in different places. So yeah, that's we're not going to, the 0 vector is just a vector of 0 is fine. You can think of position vectors. Again, it doesn't matter. This whole bit of text, we should update it, and I'm sorry, it's not very suitable for us. But here we are with the norm, which we spoke about before. Okay. Now we can add vectors, which in the way we're teaching things here, there's a question, we don't have LU decomposition. No, LU decomposition is taught in Math7501 in a numerical context. It's typically taught there. Okay, so you can think of vector addition just like we had matrix addition, add the coordinates fine, and vectors are, all these properties hold. Sorry, this is not, we already did this in the context of matrices, and you could think of vectors as a special case. But when you think of scalar multiplication of a vector, then you're stretching the vector. That's fine. And a unit vector, when you're speaking in 2 dimensions, and you'll see some of this in like these videos. So if you look like at this video, the 3 blue 1 brown, the 3 blue 1 brown video, then they use notation that's common in engineering courses, which is to call this vector I and this vector J. Okay. Yeah, I and J might mean different things, different concepts, but that's the vector I and J. So that's when you're in R2. What other notation did we have for these 2 vectors before? What would we call them? Yep, E1 and E2, right? That's what we would call them. Okay. It's kind of nice to know that any vector V can be written as a sum of this vector V1, sorry, this vector that has the first coordinate of V. Let me just color code this so it'll be clear. Sorry, let's undo a bit. So let's call this V1. Well, that's what it's called. And let's call this blue one below V2. Okay, so V2 is here and V1 is here, right? So V, you can just put a sum of 2 vectors that only have 1 coordinate, but then you could have written this as V1, the scalar V1 times I, or E1 if you'd prefer that notation, plus the scalar V2 times E2. Okay, you could have written it like that. So that's kind of nice to say that any vector that sits here is kind of like a combination of this component and that component. And a lot of what you'll do in linear algebra and Math7501 is, and in general, is not represent a vector using this standard basis of E1 and E2 or I and J, but rather a different basis. Okay. Yeah, let's skip this. And let's skip this as well. And now we speak about vectors in Rn. So in general, R, now I've said it implicitly, but this R, that's a set of real numbers. And when you put an n up here, what you mean is you mean the Cartesian product, and we'll actually define this very precisely in the unit after the next unit, is the Cartesian product of R with itself. So this is a space of n-dimensional vectors. Okay, so vectors in Rn. All right, this is an n-dimensional vector. Again, some people call this in some text an n vector. Okay, and you can do everything with vectors in Rn as you did in vectors in R2, but you've seen that already before. So this is also a bit repetitive, and so is this. I'm sorry. Okay. This just, to call this a theorem is a bit much, but every vector is in Rn is expressible in terms of the vector of the special vectors E1 up to En, just using this decomposition. So this decomposition is kind of important in further linear algebra, right? So you can take a vector V and you could say, hey, it's going to be sometimes you'd call this a linear combination of n vectors. And is this a vector space? Well, E1 up to En, that set of vectors, the set of vectors spanned all the linear combinations of E1 up to En is a vector space. And so is Rn is a vector space, but we're not defining vector space in this course just yet. Okay. Now in R3, people sometimes use I and J and K, so you might see that. So that's things you could still draw if you really try and visualize in 3 dimensions. Okay. The inner product of 2 vectors is 0. You could see this in R, you can see this geometrically in R2 and R3 if they're perpendicular. Okay, so that's the only case where the inner product is 0. Okay. And this is again somewhat repetitive, and I won't use this notation because it doesn't fully agree with what we're using. Okay, now the cosine of theta between 2 vectors is the inner product normalized by the norms. But again, you'll see more of this in Math7501 with a bit more substance. Okay, And similarly, sorry, I'm skipping a lot of things. The projection formula as well, we'll see it in much greater depth in MATH7502. So that's it. I guess the last thing is what we could stop in is on this properties of dot product. So you've seen dot product already, but let's look at this property from the viewpoint of matrices. Okay. So how do I represent U dot V in terms of matrices? If I want kind of to think of U and V as column, as matrices, as n by 1 matrices. How do I represent this? I've already had this. What's U dot V? How can I do it with a transposed? U transpose V, right? It's U transpose V. So you can call this a dot product or an inner product, okay? What is the dimension of this thing I'm putting a box on, or what are the size of this? What kind of object is this? What is this? Is this a matrix, a vector, a scalar? What is this thing? It's a scalar, right? It's a scalar. So a scalar, what's a scalar transposed? What's the number 17 transposed? Not 17 inverse. It's 17, okay? Because, yeah, right? So it's not transposed inverse, right? So this should also equal, according to just the rules of matrices, so we thought of, that's also U transpose V transposed. So then you can take a scalar and transpose it. The scalar just standing there and saying, it doesn't bother me. I'm a scalar. Go ahead, transpose me. I don't care. Okay. But now you remember the rules of transpose. Now think of these guys as matrices. This is a matrix and this is a matrix. Okay. And you can do multiplication in this matrix because the inner dimension is 1. Okay. This matrix is like that. And this, so the left matrix, this is like a row and this is a column. Okay. That's what you can do. So what is the matrix A times B transposed? We had that. But at, I like this answer. But at, B transposed, A transposed, but at. That's a good rule. All right, so let's apply this. So this is going to be V transposed times U transpose transposed. What's U transpose transposed? U. So that's V transposed U. Okay, so, and that, according, if we just use this thing, it's just V dot U. Okay, so yeah, dot product is commutative. Okay, there wasn't a whole lot in this, but we just see that everything agrees with the rules. All right, dot product distributes, just like here. Again, think of this as matrices. So if you want, this will be V transposed times W plus U. Okay, and matrix multiplication distributes, right? So that's V transpose W plus V transpose U, and that's what you have here. That's it. And the scalar, the third rule, is that the scalar can come out of the dot product or can go in anywhere, sure, because it's just a scalar floating around. And the fourth rule is, well, look, V dot V is the sum of VI squared, is the sum of squared, right? The only way that this is going to be 0 is if all of the entries are 0, right? When you're summing a bunch of things that are non-negative, because these things are non-negative, these are squares, if the sum is 0, it means that all these are 0. Okay, so it's clear that 0 transpose 0 equals 0. That's fine. But what we have here is that if V transpose V equals the scalar 0, then V equals the vector 0. Okay, this is 0 scalar. This is 0 vector. Oops, sorry, I jumped. Okay, 0 is a very overloaded character. Okay, this is 0 scalar, 0 vector. I hope that makes sense. So there's a lot here. It's not bells and whistles, but that's pretty much, we're going on to the next unit. That's pretty much all that we have for vectors and matrices. let's see, we're in 6:36. I want to just use the next 14 minutes for just a bit more though, okay? Just a bit more, so just a few more things. So I'll just go down here and add a bit more. So this is kind of like this pre-linear algebra that you're doing. Okay, and the reason you need this is when you get to, I mean, you already saw the k-means, but quite a few machine learning algorithms, etc. Even if you just want to understand the algorithms, let's say you're not dying to understand the theory behind it, but you just want to understand what the algorithm is about, they'll deal with these types of computations of vectors and matrices. Okay, now there's a question, squared. Anything skipped won't be accessible. In this case, yes. I mean, the things I skipped here are not accessible. There will be situations where we say, hey, we didn't cover this, but that is accessible. So you don't have a promise from me, hey, whatever we don't say, we don't assess on, but we'll tell you if that's the case, okay? So anything skipped and that we don't say, hey, read that because we didn't cover it is not accessible. And yes, so this material skipped there is not accessible, okay? So just a bit more. So we had inner product, okay? Inner product, which we can just call here the dot product. Okay, in slightly more fancy mathematics, there's sometimes a distinction between the two, but for us, inner product is the dot product, right? And that was U transpose V, or U dot V, or sum I1. Let me write a bit nicer. 1 to n of Ui times Vi. Okay, so that's it. That's the inner product. And it is a scalar. Let's now speak about a friend, which is called the outer product. And by the way, in both cases, U and V are elements of Rn, and this meaning of elements and this notation you'll see in the next unit. Okay, so that means that they're n-dimensional vectors. Okay. Oh yeah, and there's another question, and sometimes people write this as U comma V, like that, with these angle brackets, especially people in physics, okay, or physically inspired. So it's called a bracket, okay? This thing is called the bra, this bit, and this thing is called the ket, okay? So, but we won't use that notation. Thanks for asking. All right. Bra, sorry, let's do it like this. Bra and ket, roughly. Okay, so that these are different notations for the same thing. Now, there is another thing you can do with the vectors, all right? Outer product, outer product. An outer product is going to be U times V transposed. Okay, I'm going to highlight. Inner product was U transpose V. Outer product was U V transpose. What is this? What is this object? What's the dimension of this? What do we, I mean, this was a scalar. What is this? What's the outer product? It's an n by n matrix. Okay, so it's an n by n matrix. Thanks for answering. Okay, just to see it's an n by n matrix, I mean, if you want, let's write it. U1, U2, U3, up to Un. That's a matrix. That's a n by 1 matrix, which is also a vector in Rn. Okay, and we're multiplying it by the matrix V1, V2, up to Vn. Okay, This is this whole thing, that's V transposed, okay? This thing is 1 by n. Okay, so you know that when you multiply two matrices, their inner dimension here works, and then you get, like was said, an n by n matrix. But it's kind of a boring matrix. It's kind of a boring matrix. What's this? What's the first entry of this matrix? I mean, it's both boring yet extremely important for mathematical data science. What's this first entry of this matrix? What's this? What's the first thing? Just give me a mathematical expression. It's U1 V1. Thank you. Because what you're doing is you're running over the whole row of this matrix. Well, but the whole row is just going to be this one line. And the whole column of this matrix. Okay, so this thing is U1 V1. What's the general ijth entry? This is ijth entry. What's the general? It's U J, Vj. Okay, so it's a matrix where the entries are just kind of all of the possible combinations. Okay, this matrix is sometimes called a rank 1 matrix, because when you do more advanced linear algebra, well, MATH7501 linear algebra, you learn about the rank. And this matrix, the rank is in a sense the number of the bits of information in this matrix. Look, it's taken n squared space, right? If n is 10, this matrix is taking 100 spots, but it's only made out of 20 pieces of information. A lot of linear algebra associated with data science deals with taking a matrix and approximating it by a combination of a few rank 1 matrices, a few outer products, okay? So this is one thing I wanted you to know, okay? Just outer product. And the reason it is, it's nothing more than just, you know, here's some operations and that's an outer product. There'll be, when you do more linear algebra, there are more properties of outer products or rank 1 matrices that you could work on. Any questions about outer product? Okay. Now, the next thing I want us to do before we leave this unit, because we'll start the next unit just after the break, okay? And this is also important, and it's not in the notes. It's 4 ways to think of matrix multiplication. Okay. Let's add some pages and let's do this. 4 ways to think of matrix multiplication. So we're speaking about the matrix A times B, okay? Matrix A times B. And if you don't mind, the matrix A, I will represent it in 2 different ways. I mean, and same for B. So I'm going to represent A as A1, A2, up to A. So let's just give it dimensions. So let's say this is M by N, and B is N by P. Okay? So N is our common, oops, sorry. N is our common dimension, right? So let's represent the matrix A is A1, the column A1, A2, up to the column AN. Okay, that's one way of representing. So each one of the A's is a column. Okay, an alternative way to represent it is, let's represent it by the row A1, but let's do A1 tilde. Okay, so that tilde implies it's a row. A2 tilde. Okay, up to A. You tell me what's going to be the last one? A what tilde? What's the last row? A tilde. What's the index? AM tilde. Well done. AM tilde. Okay. So these are 2 ways to represent the matrix A. And similarly, I'll do it very quickly. So we have it for B, B1, up to B. What's in B? What's the last row in B? BP. Thank you. And we'll also represent B as B1, tilde up to B, what's the last thing here? Bn tilde. Well done. Okay, all very basic, but we need to be precise. Now look, there are 4 ways to think of matrix multiplication. We only defined one way, and our way was to say that so way 1, which was the inner product, way was to say that A, B, ij, the ijth entry, was the inner product of what? It was the inner product of this ith row. So it was A I tilde transpose, that's the inner product, times B J. Right? That's exactly how we define matrix multiplication. Right? Because we took the ith row, I'm going to make a little scratch here, the ith row, and the bth column, and that was the thing. Okay, so I'll delete now these just so it stays clean. Okay, but there's actually a different way. Here's way 2. And this is linear combination of calls. Let's see that. So what I'm saying is that AB, the product AB, is now going to be A applied to the vector B1. And this is going to be the first column of the product. Okay, so you see A times B1, that's what you get as the first column. And then you get A times B2. And then you go all the way to A times, how many B's are there? A times BP. Okay. So what we do in this way, and you can check that these 2 ways agree. What we do in the second way is we exactly look at B this way. We splice B, instead of B here, let me just do it in red over, that's the power of the colors. So we have a B and we suddenly think of it as B1 up to BP. And then A multiplies, is applied to each of the vectors of B. Okay? And I see Casey has good memories. Superb. All right, so that's way 2. All right? Now, in linear algebra or working with matrices, whenever you can do something with the rows you can also always do it with the columns. Yeah, that's often the case for many students. And whenever you can do something, this comment just on the chat, and whenever you can do something with the columns, you can do it for the rows. So way 3 is linear on rows. So then we have to revert the roles of A and B. So what I'm saying is that AB is going to be A tilde. It's like this row now. 1 applied to the right from B. Right? This is a matrix applied on a column vector. This is a matrix applied from the right on a row vector. And that's going to be this first row. And A tilde 2 applied to B up to, how many A's are there? A tilde what? How many A's? M. Thank you. A tilde M applied to B. Okay, so I mean, this, by the way, means you can try this in Mathematica if you feel you want to. I actually maybe go ahead and try. Go to Mathematica, look at matrix multiplication, and then break up the matrix A and B according to these different columns and rows, and see that this would give you the same thing. That's maybe one very basic thing to do. Okay. I can't seem to be able to put an extra page here. This software has bugs. Let's see. Maybe no. Maybe no. Okay. Now the way 4 is sum of outer products. This way is kind of cool. So look, you have here the A and the B's, okay? How can you do an outer product? We just spoke about an outer product. Who has a suggestion for some outer products that can happen here? For an outer product, we need a column times a row. Okay. So what you can do in way 4 is you can say, I'm going to multiply this guy by this guy. Okay. And then I'm going to multiply this guy by this guy. And each one of those is going to give me a rank 1 matrix, an outer product, but I'll sum them up. And it turns out that this is the same thing. So all I'm going to say is that AB equals A1 tilde times B1 plus A2 tilde times B2 plus the last one, AM tilde, sorry, now I'm getting worried, I'm getting worried. I made a mistake. It's not, it's outer product. Needs to be this times this, and this times this, and this times this, because I know that the variable we're running on has to be of size n, okay? So I'll fix this. Sorry, so this is a mistake, this bit. So it's going to be A1 times B1 tilde. That's an outer product, okay? Because this guy is a column and this guy is a row. Plus A2 times B2 tilde plus all the way to AN times BN tilde. Okay. Now, remember, in the outer product, each one of these, so here you have a whole matrix, right? So what you've done is you've broken up with this 4th way, you've broken up this matrix multiplication into a sum of n different matrices, but each one of those n different matrices is rather simple. So that way is kind of exciting. That's way 4. That's it. That's all I want to say on linear algebra. I suggest take this thing in with these 4 ways. It'll just be kind of indoctrinating yourself a bit more with matrix multiplication. Matrix multiplication might seem, in a sense, well, it's simple. We just have a formula, but there's actually to think about what's happening with the mechanics there, and you'll see more applications. Any questions before the break? The break should have started 4 minutes ago. Yes, access to annotated notes. So I think today I put enough junk on the notes for me to actually save them and upload them to GitHub. So they'll be on GitHub. Okay, thanks for asking. Wicked. Yeah, more questions? All right, so let's take a 10-minute break. So we start in 7:05. That's 5:05 in the afternoon in China, 2.5 hours before that in India. Okay, see you in 10 minutes. Bye, guys. Bye. See you in 10 minutes. Hey, we'll start in about 4 minutes, just under. Oh, so I see a nice comment. I want to build a discussion group for MATH7501 on WeChat. If you're interested, please add this WeChat number. Good stuff. I recommend. I've used WeChat a bit. This is not for a discussion group for the lecture, but I just recommend. I just say I've used. Let me suggest this comment by Hang. Thanks for sharing. Do this also. I suggest this to the people that are not in China as well. It's clear that WeChat is very popular in China, but you can try it. This discussion group. If somebody wants to use a different medium because you don't like WeChat, also good. Questions? Oh, really? You cannot install WeChat in India? Is this kind of part of the India-China issues? Oh, that's interesting. Is that the case? Is WeChat not available in India? Okay. Well, in this course, we make peace. We're all one earth, and we chat in class. You can also use something else if you guys want. I must say Slack, when I ran this course for the first time, Slack is kind of the top, really professional way to discuss. You also get a bit of experience in Slack. It's used in industry a lot. Oh, if somebody wants to set up Slack just between the students, you can do as well. Good thing with Slack is you can have multiple channels on the workspace and stuff like that. What's the question about connecting the VPN? Yeah, okay. Discord. It's one of those things. Maybe we could have start 5 different things and find a way. There's also Piazza, by the way. Did the lecture stop? Oh, we're just in a break. The break is finished right now. You can hear me, right? See me, move, etc. Yeah, good. Okay, it's 7:05 and yeah. Just to that comment about Slack. So I use Slack professionally without paying for quite a few research projects. It has never reached the issue of I don't know. Maybe I just haven't used it enough. So I found the free version good enough for my purposes. Okay, guys. So you can continue on the groups, and I'll continue on the sets. But I'm glad there's discussion on it. All right, so we're in Unit 2. Unit 2 is completely different. This comes from the world of discrete math, from foundations of mathematics. We're going to speak about things that seem very elementary, but are very important. And the discussion will be on sets and counting how many elements are in these sets, or counting in general, Cardinality is a more fancy way for counting, especially important if the sets are of infinite size. Okay. Now, some things here are written perhaps not in the best way. Recall the notation, but we didn't speak about this notation before. So let's just say what it is. So a set is a collection of elements, okay? A set is a collection of elements. That's what a set is. And it's one of the most basic things in mathematics, okay? And when you see the sign, what you're saying, this is A is an element of S, okay, of the set S. A is an element of the set S, so that's this in, okay? Or you could say that A belongs to S. A is one of the elements of S, okay? Now, you can list the elements of a set in mathematics with these curly braces. Now, in Mathematica, in the software, the curly braces mean something else. They denote the list. But in mathematics, they mean a set, okay? So the lists in Mathematica are not sets. We'll get to that, okay? Notice that mathematically, the set x1, x2, x3 is the same as the set x3, x1, x2, okay? All right. So x1, x2, x3 is the same as x3, x1, x2. So the order of the elements of the set does not matter. Okay. And if you happen to say, oh, sorry, I jumped here. If you happen to say, repeat an element when you're denoting the set, then it doesn't do anything. So this A appears twice. So this is just a set AB. So a set is a collection of elements. There is no explicit order of the elements. Okay. The empty set is a set with no elements, and you denote it like that with a 0 and a slash in the middle. That's an empty set. Okay. And the cardinality of a set is the number of elements in the set. Okay, now some sets will be infinite, so the number, there's not really a number, but there'll still be meaning of cardinality, and we denote it like that. Okay, that's in cardinality. Okay. Now, in Mathematica, there are some functions for sets that deal with sets. We'll get to that, union, for example, or member Q. Okay, but again, this is not exactly a set in Mathematica. This is a list. Programmatically, this is a list. Okay, let's start with actually a few examples, and this is kind of very question oriented. So question A: how many elements does the set 2, 2, 2 have? 2. What are those elements? 2, and the set with the element 2, right? So thanks a lot, you're both correct. So you see this thing equals the set 2 and set 2, okay? So this in itself is, so this, I'm writing sloppily, excuse me. So this does not equal this, okay? So hence, the answer is 2. So, oops, I'm sorry. So you could have written the cardinality of this equals 2. B, true or false? True. Okay. C, true or false? C. True. Okay. Now, a set like this one is called a singleton. Singleton. It's a set with only one element. D, true or false? False. Because this set here is a singleton, which whose only element is also a singleton, and that has 1. What if I was in D going to put like this? True or false? No? True, 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 true. Yep, attack the keyboard, go for it. All right. And what if I was to put this? So if you put a line like that, that just means 1 is not an element of this set. True or false? True. Good. All right. Describe the following sets in words. That's not hard. A is the set of integers between 1 and 100. Okay. But with B, now you have a different notation. Okay. Let's look at this notation. So when you have curly braces like that, well, let's just use this one here. When you have something here, colon, or sometimes you'd put a line and not a colon, but it's the same. Then you put a condition. So that reads as all of the elements of the set R is the set of real numbers, okay? It's a very big set. It's a set of all of the numbers. Here is 0, here is +10, here is -20, but it goes on forever and it's very dense. There's quite a lot of things, okay? A lot of things in R, infinitely many things, too many infinitely many things, okay? So X in R such that X is positive, okay? Let's call this set W, okay? And tell me if it's true or false. Is 0 an element of W? Is 0 an element of W? Nope, nope, no. F, no? Okay, all kinds of variants of no you're giving me. That's very good. Okay, how about, yeah, okay, I think you understand. All right, let's go to this third set. This Z plus is the positive integers. It's actually depends. You need to be careful, and I'm not sure how we define it here. So Z, when you see this Z, this is a set of integers. Okay, so Z is a set -3, -2, -1, 0, 1, 2, 3, goes on forever. Okay, so Z is like on the number line, etc. The Z plus is only these guys. Okay, and you need to be careful if 0 is in Z plus or not. Okay, but now the way we're doing C is, and so I'm not sure, it depends per definition. Okay, so on the context, and we didn't define it here. So we're saying all of the elements of Z plus, all of the Y's in Z plus, such that Y is between -3 and 3. So what are the elements of C? So assume now that Z plus is 0, 1, 2, 3. Okay, all of the non-negative integers. Okay, okay, so in that case, it also has a 0 or no. Okay, that's good enough. So sets, good, seems simple, and it is. It is, we just need to be precise about what we're doing. Okay, next statement. If A and B are any sets, A is called a subset of B, and you put A and you put like this symbol B, if every element of A is also an element of B. Okay, so the illustration is this is B, and this is A. Okay, so when we draw things like that, this is sometimes called a Venn diagram. Okay, and it speaks about the sets as you think they're points in space, but it can be more abstract than that. Okay, so you say that A is a subset of B because if every element of A, if something is here, then it's also in B. Okay, now sometimes we use this notation, sometimes we use A subset of B, but they mean the same thing. So in most, unless somebody uses a slightly different notation. Okay, so it's not like in less than and less and strictly less than or less than equal that has that. Okay, now listen, so Casey, you're giving comments. I think maybe, are you having a private chat and a combinations chat? So I think maybe you're writing to everybody and to somebody privately. This is a, no, did I not understand? This is I think, oh, it's to everyone, so I didn't understand. So tell me.
Yeah, so I think someone else had a doubt whether 0 was a part of Z plus or not. So I was just trying to answer that.
Oh, sorry. Okay. Sorry, I misunderstood. I thought you were kind of chatting with somebody about the Slack and things like that. Okay, no, so I actually don't know. Okay, so it depends on how it's defined here. And I don't know. Okay, so I'm sorry. When it'll matter, we'll say, but let's assume here that Z plus has 0 in it. Okay, sorry about misunderstanding your question. All right, thanks. Continue on with that. All right, so this A is a subset of B. What I'm saying is that sometimes you use this notation and sometimes you use like with this one under, but it's the same. Okay, so every element of A is an element of B. So that's what we mean by a subset. Oh, now here I added all these extra white pages by accident. Let's see. So to say that something is a proper subset, proper means that A is a subset of B, meaning that every element of A is a subset of B, and A is also not B. Okay, so that means that there is some element, whoops, this would be B, this would be A. That means that there is some element here. Okay, that makes it a proper subset. But still keep in mind, we still use the same notation. We don't play around with adding or taking that one away. Okay, and Julian put something in there. So what's Z plus? So Z plus is a set of strictly positive integers? Sure, okay. But some people, okay, thanks for putting that. But some people would interpret these things differently. So when you put a plus in mathematical text, there's ambiguity, so we need to kind of know. Thanks for looking that up. But again, this is something that's kind of not universally confirmed or agreed upon. And now two sets are equal if they're each a subset of each other. Okay, so set A equals B if A is an element, if A is a subset of B and B is a subset of A. Okay, let's just see some examples. Okay, so let's say A would be made out of the elements little a, little b, little c, little d, and this is B and this is C. Okay, let's see. Is it true that B is a subset of A? Is B a subset of A? It's false. Why is it false? Because of this E. Not every element of B is an element of A. Okay. Okay. Is it true that A is a subset of C? Okay, it's true. And let's do a question B prime. Is A an element of C? I don't see. Okay. Yes, no. No, yes. Okay. A is a subset of C. It's not an element of C. So while this notation of a subset and this notation of element mean that, this guy is a papa on the right and this is a child on the left, they mean different things, okay? There is no element of the set C. There's not an element of the set C that looks like A, okay? All right, so that's false. This one, that was true, that was false, okay? Is A a proper subset of C? Yes. Okay, true. Is it true that B is a subset of B? Yes. Every set is a subset of itself. That's for every B. Okay. Okay. Draw a Venn diagram to the representation between the following sets: 1, 2, 3, 1, 4, and 2, 3. Okay, so let's try and do this. Let's do 1, 2, 3. That's the set A. 1 and 4. That's the set B. And 2 and 3 is the set C. Okay. Is C a subset of A? Is C a subset of A in this Venn diagram or in this world? Yes. Is A a subset of B? No. Okay, good. Some more. Why not? True or false? The singleton with 4 is an element of the set that has 1 and the singleton of 3 and 4. We got N, no, no, N, T, N, false, N, F, F, yes, a bit of yes. Okay, no, this is false. This is false. There is no this, but look at the second one. What about the second one? What about the second one? This one now. This guy. True or false? B. Is B true or false? T true, I see. Is B true or false? So the singleton 4 is a subset of the set 4. Yes, because every element of this thing, and in this case there's only 4, is an element of that. Okay, true. Okay. So you see, 4 was a this set of 4 was not an element of this set, but was a subset. Is this true? So that's true. How about C? Keyboard away, go for it, true. And how about D? Does D even compile? Is D is like a syntax error. Why is it a syntax error? Why is this? This is very embarrassed to have this. Why shouldn't I? It's not a set, right? And the subset guy wants a set on the left, set on the right. So it's like false with, you know, dark F, like bad false. Okay. Okay. Note the set notation used here verbally read it as such that, okay. So here's an example. Let's skip this example, just so not to get stuck on the number theory stuff, and we'll get back to it next week. Okay. Now operations on sets. So good, we know how to do, at least we know how to check if a set is a subset of another set. Good, we know the set elements. Now some operations. Now, when you do operations on sets, sometimes you define something which you'll call the universal set. And that's often we use sets in probability, not always, but one of the uses of sets in probability, almost in anything in mathematics. At the end of this unit, we'll show an optimization problem that's used sometimes for forms of scheduling. That's called a set cover problem, okay? But which is not in probability. But in probability, you use something called the universal set, which is all possible outcomes that can happen in an experiment. So just keep in mind that there might be like a universal set, which is like everything. Okay. So suppose A and B are subsets of the universal set. I can write this as just A, and sometimes we put A comma B, subsets of the universal set. So the union of two sets, and that's denoted that with this cup, this union, okay, is the set of all elements in the universal set, such that X, this should have been a little x, and a little x is in A, little x in B, or in both. Okay, so that's the union, all right? The intersection is something that's going to be a bit smaller, quote unquote smaller, okay? Is the set of all elements such that they're both in A and B. And the set difference is going to be all of the things that are in B and not in A. Okay, we'll get to that. And the complement is, this is where you really need a universal set. Okay, for a complement is everything that's not in the set. So the complement of the set. Okay. So here's actually ways to write this. So A union B are all of the x's of the universal such that x is in A or x is in B. And when we say mathematically or, we mean or this is correct, or this is correct, or they're both correct. Okay. Here it's an and. Okay, so this intersection is an and. The B minus A Sometimes we put like slash minus. It's nicer. Okay, be just a way of notation. Is all of the x's that are in B and not in A. And the A complements are all of the things that are not in A and are in the universal set. Okay. Armed with these operations, let's get to business. Let the universal set be 1 to 10. The numbers 1 to 10. And let A be the first 4 numbers, and let B be the even numbers in there, okay? And C the odd numbers, right? 1, 3, 5, 7, 9. Okay, we can describe what these sets are. Write the following sets. A intersection B. Go for it. A intersection B. All of the elements that are both here and here. Okay, we seem to have agreement. 2, 4. A union B. Let me just write this. I'll just take everything that's either here or here. So the way to do it is just do 1, 2, 3, 4, 6, 8, 10. Unless I made a mistake. Good. B union C. What's B union C? U. That's a nice way to write it. U. Like the universal set. Okay. This is U. Everything. Okay. By the way, in this case, B and C are called a partition. B and C, we'll get to that, but I'm just saying now, are a partition of U. A partition is a collection of 2 sets that are disjoint whose union is the whole bigger set. Okay, a disjoint means their intersection is 0. We'll get to that. Okay, B minus A, we can also put the minus like that. B minus A. So what's B minus A? 6, 8, and 10. Okay, I agree, that's B minus A. Now look, when you have a universal set, can you tell me how to write B minus A with intersection and complement without using, I don't want to use the minus sign. How do I write this when there's a universal set? How can I do this in terms of B and A and something like that? Does anybody have an idea? So I want to write, I want to say that B minus A, yeah. I want to say that B minus A is some operation that will involve, oh, sorry. Fill in the blank. It'll have a B, it'll have an A, and it'll have, fill in here some operation here, and maybe fill in something up here needed, something up here needed. You remember the complement, which, by the way, complement, sometimes you can put a bar over. That's a different notation for it, but the complement of the set. So how can you do B minus A by filling out these 3 yellow things? I hope you can. Maybe I'm making a mistake. This one, and this one, and this one. Maybe some of them would be empty. So let's think. We want, okay. Oh, I like the way you did this intersection. B intersection. Yes, A complement. So that means everything that is in B and not in A. That's the same. Good. Got it? B minus A is B intersection A complement. Okay. If you B minus A, I'll just write it, is B intersection A complement. If you don't have a universal set, then you can't do a complement, and then you really need a B minus A. What I mean I don't have, if you're in a setup where you're not speaking about a universal set. Okay, A minus C. Back to the smaller stuff. What's A minus C? So A minus C, there are claims that it is 2, 4. Let's see. So everything that is in A and not in C. Yes. B complement. What's B complement? One character for B complement. Yep, KC, thank you. You even have it in your initials. That's a C. Okay, and A complement. A complement we need to write. We can't really, we need to write. Okay, so that's the, let's write A complement like that, 5 to 10. So we'll write all of the X in U such that X is greater or equal than 5. Okay. A complement, getting tired from this. A complement union B. So add to the A complement in B. So add to this also the 2 and the 4. Okay, add. Okay, this you're feeling yourself. Good. So that's sets and operations with sets. All right. And you saw this bit, which maybe you just had to think about just a bit, etc. All right. Now, moving on from sets, and we'll come back, sets are in there, but there is something called an n-tuple, which in a sense is like a vector, but we don't think of it as a vector in space or anything like that. Okay, so when you have elements like that, sorry, let me write it like this. So we're moving on to the next thing. So when these are elements x1 through xn, and they're not necessarily distinct, okay? So they can be, you know, repeated, right? In sets, they had to be distinct. Then an n-tuple is just an ordered list of this element, and you put it like this. Some of you are doing Python, okay? Python has tuples, okay, tuples. So a tuple in Python is just this, okay? It's kind of a fixed, okay? So it's, this thing is borrowed to Python. A 2-tuple is called an ordered pair, and a 3-tuple is called an ordered triple. Now, the thing is that the lists in Mathematica are actually like tuples, okay, because they're just collections of things. So it's, even though Mathematica tries to be very mathematical, they use a notation of curly brackets for tuples. Okay. And 2-ordered tuples are the same, sure, if they have the exact same entries for all x and y. Okay. Example 21, true or false? True or false? Okay, false. False. What if I was to put curly braces here? True or false? True. Good. So curly true and without curly false. Good. That's interesting. If, sure, what's y and z? Not a problem. Okay. What's y and what's z? Okay, so y is 3 and z is 3. Square root of that is 3. Okay, good. All right. Now we get to something neat. Given two sets, A and B. So now, okay, we had tuples. Okay, now we're getting back to sets. Now, if you have two sets, any two sets, A and B, you get this thing called the Cartesian product. Okay, of A and B, and we denote it with this A cross B. Okay, we had today, I remind you, in a different context, we had inner product, outer product. Now we're speaking about this thing called Cartesian product. There's also something called cross product, which we don't speak about. It has to do more with physical mathematics. Okay, but Cartesian product. Right? The Cartesian product is a set. It's a set. What are the types of elements of this set? What do they look like? They're tuples. Okay, and they're all the possible tuples that you get from A and from B. Okay, all of the elements of A and B. Okay, so let's just see, how do I add a page to this thing? Let's go here, add page. So let's take the set A to be my sets after so many years of mathematics look very poor. I think I will never do nice curly braces, but I will live. Okay, so what the set A will be the elements A, B, C. The set B will have 1 and 7. Okay, so let's look at the Cartesian product A cross. Sometimes we say A cross B. Okay, so that is the set of all tuples A, B. That's the definition, such that, okay, or you want the dots here, put dots, such that A, you know what, let's not confuse here because I've used ABC here, so I'll put all of the U comma V. Okay, so these are like the variables, the inner variables of the loop, if you'd like, such that U is in A and V is in B. Okay, so let's start and look at these elements. So we've got the element in there, A1, right? You agree that's an element? Can you give me another element? That's one of this tuple, this first tuple is an element of the cross product, A1. There's an element B1. There's an element C1. There's an element A7. There's an element B7, comma, and there's an element C7, right? That's what you said. Okay. Now you can view this as also you can just put it like that if you want. When you do this cross product, you could have put an A, B, C, and say a 1 and a 7, and you put them like this, just drawing schematically, and you put all of the tuples here. Okay, these 1, 2, 3, 4, 5, 6 tuples. Okay, so this is a cross product. Right? Now, sometimes there's a cross product between two sets, but sometimes you have a cross product between the Cartesian product, some cross product, okay, between, sorry, am I making a mistake? The Cartesian product, cross product I just said is something else. Is a Cartesian product between n different sets, okay? So it's like you put this in the first coordinate, this in the second, up to that in the nth coordinate, okay? Now look, if all these sets happen to be the same set, then just notationally, let's say if the set A was 1, 2, 3, then we can speak about the set A squared. A squared is just shorthand for A cross A, okay? And that is a set that has 1, 1, 1, 2, 1, 3, 1, 2, 1. I'll just write it all, 2, 2, 2, 3. If you need to do this in a quiz, make sure you're precise about the round brackets and the curly brackets. Okay, well, have better calligraphy than me. 3, 1, 3, 2, 3, 3, or not. Just stay with bad calligraphy, but be precise. Okay, so that is A squared. At this point, you can understand what we mean by Rn. Now connecting it to the previous unit. What do we mean by Rn? It's the Cartesian product of the set of real numbers with itself, with itself, with itself, with itself, with itself. You see, that's how we get an n-dimensional vector. Capiche? That's Rn. Is that clear? So that's why the notation Rn comes from at least this kind of Cartesian product thing. Okay. This example, we effectively did this type of thing. So let's move on. Okay. So recall that denote the set with no elements in it is an empty set. Okay. The empty set is, the empty set is a subset of any set. Is it true that the empty set is an element of any set? If S is some set, is this true? Is the empty set an element of any set? False. No. I see an F and I see a no. I just see two respondents. Is an empty set an element of any set? Just two. That's it. Everybody else gave up. No. 52 people. Yes. Okay. At least we get it. Okay. Some didn't give up, but are no. So it's wrong. So this is not correct. That's not correct. Okay. So the empty set is not an element of every set, but it's a subset of every set. Okay. Again, to see if something is an element, you need to open up the set and see what's inside. Does it have something in it that is the empty set? Okay. To see that this holds, you need to see that every element of this thing in yellow is an element of this thing in purple. Now, there is no element of this thing in yellow, and hence, well, sure, it's true, why not? Okay, that is kind of the argument. Okay. And every set is a subset of itself, we said that. Okay. We will return to this when we speak about logic. So there's been a bit of a shuffling of the units, and some of these things are better after the logic. So we'll come back to this just a bit later, as we will to at least one exercise there. Okay, partitions. I spoke about this word before, and this is kind of an important word, partitioning. Okay, I mean, the word in English to partition means to kind of separate, right? But it mathematically, the word partition means that you separate and you get kind of a complete cover. So first of all, an auxiliary, a helping definitions. Two sets are called disjoint if and only if they have no elements in common. How do you write that in terms of intersection? Like that. Okay. The intersection of A and B is empty set, so they're disjoint. Okay. Now, a collection of many sets is called mutually disjoint or pairwise disjoint if for all the possible pairs, those intersections are empty. Okay, so that just means, you take all kinds of subsets and you say, okay, there's no connection, no shared element. And a collection of non-empty sets, okay, so they have to be not the empty set, is called a partition if their union is the whole set, a partition of A, and they're mutually disjoint. Seems like a lot of definition, but this is actually important. So this is used, okay? So look, if I take here, let's take here, the universal set has the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That we had a set like that before. A possible partition can be, this is like this set, and this set, and this set, the four sets. Okay, this is a partition, okay? This will be the set A1 would be this thing, and the set A2 will be this thing, the set A3 will be this thing, the set A4 will be this thing. So the intersection of any AI and AJ is the empty set if I is not equal to J, and the union of all of the AIs equals the whole set A, if you'd like. Okay, sometimes you can write union, you can just write that, and you could do like union over all I. Okay, so you can notationally write this as union I 1 to n of AI. It's just a different notation for the same thing, just like summation notation. Okay, I hope it's clear. Please stop me if it's not. Okay. All right, before we go to sleep, well, here in Brisbane, some of you are still starting your day. All right, determine whether the following statements are true or false. So let's do a bit of that. Is this true? A or A, true or false? False. I'm with you. A union empty set is A. You can unionize with empty set, true. Sure, because A union empty set is a collection of all of the elements that are either here or in both. And there's nothing here, but who cares? So, true. A intersection, A complement is the empty set. true. How would you say this using one word? A is, well, not using one word, but A and its complement are, A and its complement are, one word, A and its complement are no, they're not a partition, they're disjoint. They're also a partition, but then you'll need to say a partition. Yes. So A and A complement are always a partition. So it's always possible to take, like, you know, make this A and make this A complement. They're a partition of this universal set. Okay. Yeah. Now, you can only speak about complement if you define the universal set. Okay. A union A complement equals the empty set. False, right? Now, when we say this false, it's false meaning, you know, I mean, there might be sets that this is true for them. For example, if the universal set was empty set, etc., right? But this is not true for any set A, so it's false. A intersection the empty set is empty set. A intersection the empty set. I see a lowercase t, a capital T. I see some T's. A intersection the empty set is the empty set. Okay, I'm with you, true, right? So this set is a set of all elements that are both here and here. There's no elements that are here, and hence there are no elements that are in this combination set, and then hence it's an empty set. Okay. A, question somebody? I hear a mic. No, okay. A subset, A minus set minus. You got a question, Hoja? I'll mute you. Okay. Oh, you muted. Okay. Good. Okay. Just if you have a question, go for it. Okay. A set minus B. We're finished in a second. A set minus B intersection B. Is an empty set. So what is this set here? This set A minus B is all of the elements that are in A and not in B. Okay, so here we no longer have elements in B. Okay, so this is true because it is. Okay, you can also see it's true if you want using our other trick. So let's write this as this guy. I mean, this whole thing. We said that's A intersection B complement, right? That's what A minus B is. And that's intersection with B. And intersection is associative. We didn't say this, but we can do the intersection like that, or we can do the intersection like that. What's B complement intersection with B? What's this thing? It's an empty set. Okay. All right. So that's all true. Good. How about G? G? True. They're disjoint. That just means their intersection is empty set. How about these sets? Are they mutually disjoint? False. What makes false? So this set is not disjoint with this set because of the 5 of false. Okay, I think that's a lot. So we'll stop here and we'll be able to, well, then we'll go on to kind of something slightly different, and then we'll deal with counting, which will be fun. So this will be kind of more computing things. And cardinality, we'll speak about this kind of fascinating thing of if set is countable or not. And then we'll deal with something called the set cover problem, just to see that you could deal with this notation. So that's going to be all next week. Plus we'll get into unit 3, the logic. Is empty set an element or a set? The empty set is a set. The empty set is a set that has a property that no element is an element of it. Okay, that's an empty set. Yeah, set without any member. Cool. Any questions, thoughts before we part for the week? No, I must say, I don't know how you do it, students, because I now had the 2 classes. I typically don't. Very long day. You have to do this all the time, but I guess you speak a bit less. I won't be teaching data 7001, which many of you met me in the morning next week, but I'll see you in the evening. What's the question? Does n include 0? Now, okay, there's a question, does n, the set of natural numbers, you see, so here too, different communities. So don't go jumping, different communities. Some people say this is the set of natural numbers is 1, 2, 3, 4. And some people say that it's 0, 1, 2, 3, etc., or 4, etc., forever. Okay, some people use an n with a subscript 0. Okay, and that's this guy. So there's some ambiguity, just so you know. Now, there is a question, the last one by Kai. This is B the empty set? Is B the empty set? What I have here, B the empty set. B is the set that has an empty set. Is it the empty set? No, so that is not this, okay? Okay. More questions? No, so A intersect AC, no, so there's a question by Jean. So A intersect its complement is not a set with the empty set. So A intersect A complement is the empty set. I mean, there is no X. You cannot find X such that X is an A and X is an A complement, because X and A complement means that it's not an A. So you cannot find an X at both an A and not an A. Okay, now there's a question, does N has 0 or not? Does N have 0 or not? I don't know. I mean, it's just, you go to some book and it will say one thing. You go to a different book, it will say a different thing. Okay, slightly different dialects. I mean, let's be a bit forgiving for the mathematics. It's actually quite universal, but on some specific things, just some silly decisions, is N starting at 1 or starting at 0, just like with the programming languages. Okay, you have to know what it is. So, no, so last question, empty set belongs to any set. Is that right or wrong? So put some trues or falses on the last statement on the chat. Empty set belongs to any set, true or false? Empty set belongs to any set. It's false. It is not belong, it is a subset. So the word belong is like an element of. Subset is something else. Okay, so that's the two relationship. Belong is an element. Oh, so the empty set does not belong to any set. It only belongs to some silly sets like this set B that has empty set as an element. Yep, element versus subset, and belongs is an element, okay? So belong is a synonym of element. All right, everybody, have a good week. You've got assessment. This is week 2. This is one semester. This is kind of the best part of semester before you really finished and tired and demotivated. So enjoy your motivation. Go for it. Study well. Have a good one. Bye.